Have you ever stopped to wonder what the code inside a self-driving car might actually have in common with, say, the Federal Reserve? Today, we are going to look at how the exact mathematical principles governing artificial intelligence can actually be used to model human behavior and even large-scale government policy. I mean, it sounds literally like science fiction, but it's not. It's pure applied mathematics. We're going to decode the exact equations that link an individual's emotional choices to the macro decisions of an entire nation. Okay, let's dive right in with the foundational math here, stochastic control. I want you to think of this basically as the math of navigating chaos. Imagine you're driving on a completely iced-over road while blindfolded. You have to constantly adjust your steering based on incredibly imperfect feedback, just to keep the car from spinning out. Well, stochastic control is the mathematical framework we use to determine the absolute best possible path forward when the environment around us is totally unpredictable. This is the exact same math that keeps robots balanced, allows autonomous vehicles to navigate sudden traffic stops, and, as we're going to see, stabilizes entire national economies during a massive crisis. So, our roadmap for today. We'll be walking through the mathematical framework, machine inference, human fickleness, government preferences, and finally, system optimization. Part 1. The mathematical framework. We've got these 6 universal mathematical variables that govern pretty much all dynamic systems. Think of them as lenses. You have states, which is the true, often hidden reality of a situation. Controls, those are the physical interventions or policy actions you take to actually change that reality. You have measurements, which is the imperfect sensor data you manage to gather. And then you have parameters, distributions, and errors or noises, and those represent the universe's inherent randomness. Think of a simple thermostat trying to heat a really drafty house, right? It measures the air, adjusts the heat, and constantly fights the unpredictable cold drafts coming through the windows. Every single decision-making model out there, whether it's a human, a machine, or a massive institution, uses these exact 6 lenses to map out reality. Moving on to part 2, machine inference. Now, we really have to draw a line between generative AI, the large language models we're all chatting with online, and physical AI, like robotics. Generative AI is fundamentally just minimizing error to predict the next word based on context. It maps contextual correlations via gradient descent. But physical AI? That operates in the messy, incredibly unpredictable real world. It continuously updates its control policies, those physical interventions we just talked about, to navigate a physical environment toward a very explicit goal. It uses reinforcement learning to dynamically control its actual physical actions in real time, responding to gravity, friction, moving obstacles, the whole shebang. Part 3. Human fickleness. Now here is the absolute core thesis of all this. Unlike AI, when we build behavioral models for the human brain, we have to account for, well, emotions. Humans wake up grumpy, right? We have psychological biases. We change our minds for seemingly absolutely no logical reason. In system equations, mathematicians actually call this endogenous noise. This fickleness acts as a completely unique, irregular layer of mathematical uncertainty that literally must be systematically added into the behavioral model. A machine's noise comes from, say, a faulty external sensor or a dirty camera lens. But a human's noise? That comes from within. So how in the world do we function with all that internal noise? Well, the human brain acts as this incredible adaptive learning engine. First, we take in sensory measurements from the world around us. Then our brain acts like what's called an extended Kalman filter. I like to think of it as mathematical noise-canceling headphones, just filtering out the bad data and helping us focus on the real signal. And finally, we perform a Bayesian update. What that means is we are continuously modifying and revising our internal parameters based on new experiences. Every interaction serves as a data point, allowing us to adjust our prior beliefs and optimize our decisions, even while dealing with the constant, unpredictable hum of our own emotional fickleness. Which brings us to part 4, government preferences. This is where we get to scale things up. There is a really fascinating 2004 paper by Sung-Rae Kim, and what this paper did was honestly groundbreaking. It merged optimal control models, again, the exact same math you'd use to continuously steer a rocket ship, with dynamic computable general equilibrium, or CGE models. Now, a CGE model essentially maps the entire complex network of a national economy, looking at how different sectors, from manufacturing to agriculture, interact with one another. What this paper did was apply engineering-level steering mechanisms directly to macroeconomic policy, factoring in those specific layers of human uncertainty and learning we just defined. Here's the thing. Governments are optimizing agents too, just like an AI or a human, but they obviously don't operate on pure robotic logic. Their behavior is mathematically shaped by the political economy. Their political preferences, like wanting to aggressively support green energy over fossil fuels or prioritizing employment in specific sectors, they literally act as weight parameters in their optimization algorithms. Specifically, these sit within what is known as a linear quadratic regulator, or LQR objective function. So politics essentially becomes a hard mathematical variable that steers the entire government system. And you can actually see this math at work when looking at the optimal control paths for things like GDP, employment, and pollution. Different political preference schemes completely shift the entire optimal trajectory of an economy over time. For example, if a government places a heavier mathematical penalty weight on polluting industries, the outcome is totally different. Just by tweaking those internal political preference weights inside the LQR algorithm, the final policy outcome changes dramatically across all major economic sectors. It's wild to think about. And finally, Part 5, System Optimization. This mathematically proves what happens when governments face massive economic uncertainty. When tracing parameter uncertainty through an adaptive learning process, just like that Kalman filter we discussed earlier, it turns out that when uncertainty in the system jumps, say from 20% to 40%, optimizing governments actually hit the brakes. The optimal paths visibly flatten out. Mathematically, it proves that when the fog of uncertainty is thick, governments adapt to the lack of clear data by using their policy control instruments in a much more cautious, conservative fashion. So, whether we're talking about an AI navigating a physical maze, a person making a daily choice, or a massive government trying to stabilize a national economy, they are all literally participating in the exact same decision-making optimization behavior. AI reinforcement rewards are exactly equal to a government's political economy preferences. Machine learning weights, that's human education and continuous Bayesian updates. And sensor noise in a robot is the exact mathematical equivalent to human fickleness and endogenous noise. Individual, corporate, and government decision-making are all seamlessly governed by this one unified framework. So, we've seen that our personal fickleness, our adaptive learning, and even our most complex political choices can be accurately modeled as mathematical parameters in a grand optimization loop. Which leaves us with this final, kind of provocative thought to ponder. If your emotions, your behavioral biases, and your deeply held political beliefs are ultimately just endogenous noise and weighted parameters in a mathematical equation, how much of your choice is truly yours?